Hi, everyone. Thanks for tuning in. My name is Christopher Jung. I'm a fourth-year PhD student at Penn, where I am fortunate to be advised by Aaron Roth and Michael Kearns. Today, I'll be talking about moment multicalibration for uncertainty estimation. This is a joint work with Aaron Roth, Mallesh, Changhwa, and Rakesh, Vohra. The order of the talk will be as follows. I'll first give some motivation for this work and some quick background, and then I'll talk about what moment multicalibration means and how it can be used for uncertainty estimation. First, I'll talk about the motivation and some quick background. I'll be using this story as a running example to give some motivation for our work. Suppose a patient comes to a doctor wanting to get some prescription for a personalized drug, and the doctor needs to predict what the stable dosage is for the patient given the patient's features X. Let's suppose the doctor tells the patient her stable dosage is f of x. The patient may want to know how certain the doctor is about the prediction. So the doctor provides some variance on the prediction. But the patient may want to know a little bit more than just a variance. So the doctor provides a prediction interval, Lx and U of x. Now let's pause for a moment to think about what these numbers actually mean. In an ideal world, all those predictions would be such that the randomness is over the conditional distribution of y given x. So the f of x is the conditional mean, g of x is the conditional variance, and the prediction interval is such that the only randomness is over y given x. However, it's more likely that the randomness is actually averaging over the whole population, meaning other features as well. For instance, the mean predictor f of x is more likely just a calibrated predictor instead of just being a conditional mean. And I'll try to talk about what it means for a predictor to be calibrated later. And the variance predictor g of x is actually averaging over both y and x and measuring the variance with respect to this calibrated mean predictor. And the prediction interval is more likely just a marginal prediction interval, which is averaging its randomness over the x's. And you may ask me, why is it that you can hope to achieve this ideal version? It's because in a high dimensional setting, we would have seen each x at most once, so we can hope to make any meaningful inference on the conditional distribution y given x without making any further assumption. And there are two types of solutions people have used to bypass this. One is to make a parametric assumption about the data generation process. For instance, suppose the conditional mean is linear in terms of its features. Then you can just try to form uncertainty around your estimation on the parameter data and transform this into your uncertainty around the prediction on y given x. And the other approach is what I have alluded to before. People try to average the randomness over the whole population. And in fact, this is quite common in the calibration and conformal prediction literature. So let's go back to the story and suppose the doctor tells the patient that the provided prediction is a marginal prediction interval averaging over all the x's. In this case, the patient might rightfully so complain to the doctor, saying that she's part of the demographic group that is only less than 5% of the population. So it's totally possible that her stable dosage falls entirely outside of the provided marginal prediction interval. So instead, the patient may want to know about prediction intervals for people like herself. To that request, the doctor may provide a prediction interval for each of the group that the patient belongs to, as shown here in the slide. The patient belongs to 3 different groups, so for each of these group, doctor provides a valid marginal prediction interval, denoted as A to B for the first group, C to D for the second group, E to F for the third group. However, one problem with this is that while the patient belongs to all these 3 different groups simultaneously, the provided prediction interval may be all disjoint, meaning A, B, C, D, E, F may be all disjoint. And one way to overcome this is to simply combine all these prediction intervals, meaning you take the widest interval that encompasses all these intervals. So to this end, we want to come up with a single prediction interval for some point x, such that the prediction interval is a valid marginal prediction interval simultaneously for all the groups that the point might belong to. Because we have a single prediction interval, this avoids the need to take the widest interval if you have different disjoint prediction intervals for different groups. And you can actually average over any other group that the point may belong to, and it is guaranteed to be a valid marginal prediction interval for that specific group. Now, I'll actually talk about what moment multi-calibration means and how that can be used to give uncertainty estimation with the guarantee that I just described in the previous slide. And to do so, I'll first review what mean multi-calibration is, which was first introduced by Johnson et al., Johnson, Kim, Reingold, and Roth. And then I'll show you how you can extend this idea to higher moments, such as variance. And then finally, I'll talk about how you can use Chebyshev inequality on top of these multi-calibrated predictors to form prediction intervals with the guarantees that we just discussed before. First, mean multi-calibration. Let's assume that there is a distribution over the feature space and the label space, where the label space is just exactly the 0 to 1 interval. And we'll write mu of x to denote the conditional mean of a point x. And write mu bar to denote the predictor that is trying to emulate the true conditional mean mu. We'll also overload the notation and write mu s to denote the conditional mean on this set of points s, and mu bar of s to denote the average of our mean prediction on this set of points s. Now, we'll say our mean predictor, mu bar, is alpha mean consistent on a set S if the difference between the average of our mean prediction on this set of points, denoted as mu bar of S, and the true conditional mean on this set S, denoted as mu of S, is at most alpha scaled by the measure of this set of points. And one more notation, I'll write x mu bar I to denote the set of points whose predicted conditional mean actually falls in the ith bucket, meaning its value falls between I minus 1 over m and I over m. Finally, I can tell you what it means, what it means for mean predictor to be alpha mean multi-calibrated. No, alpha mean calibrated. We say a mean predictor mu bar is alpha mean calibrated if the predictor itself is alpha mean consistent on every x mu bar I, for every I spanning n. It's essentially guaranteeing some sort of closeness between our prediction and the true conditional mean on these sets, x mu bar 1 and so forth, all the way to x mu bar n. In other words, the true mean on the set where our predicted mean was approximately some number v, the actual true mean on this set of points is approximately v as well. And now mean multi-calibration is essentially requiring calibration over some collection of groups. And for any group G, let's kind of generalize the notation we've had before and write G mu bar I to denote all the points in group G whose predicted mean falls in the ith bucket. And we say mean predictor mu bar is alpha mean multi-calibrated with respect to some collection of groups if the predictor is alpha mean consistent on every G mu bar I. The original multi-calibration paper shows how you can achieve mean multi-calibration through a projected gradient descent approach, where they simply post-process any predictor and say that it requires n most 1 over alpha square many of rounds of fixing in order to guarantee the predictor is alpha mean multi-calibrated after the post-processing. And each projected gradient step is quite simple. We simply need to audit for any set G mu bar I on which we are not currently alpha mean consistent. And we can actually nudge our predictions on the set of points by a little bit. So if we're overestimating, we make our predictions a little bit smaller on this set of points. On the other hand, if we're underestimating, then we try to make our predictions a little bit bigger. Now, let me show you how you can extend this idea to higher moments, such as variance. First, a little bit of more notations. I'm going to write mkx to denote the kth central moment. And as before, write bar mu k to denote our prediction, moment prediction. And as before, we're going to generalize this to group of points. So write mks to denote the conditional mean on this set of points, s, and bar mk s to denote the average of our predictions on this set of points. And now we want to build a moment predictor that is quote unquote multi-calibrated with respect to this true conditional moment function mk. But what do we even mean for the moment predictor to be multi-calibrated? If we follow the same logic as before, we would want the following. For all the points whose predicted variance is approximately v, we want the true variance on these points to be approximately v as well. But it turns out this is not quite what we want. Our goal at the end of the day is to build a moment predictor that is trying to emulate the true conditional moment. But the condition above is not even satisfied by the true conditional moment function. And here's a simple example to convey this point. Suppose we have a distribution that is a uniform mixture of points x1 whose label is 0 and x2 whose label is 1. And suppose we're focused on the variance, meaning k equals 2. Note the label is determined deterministically by the feature. So in both cases, the conditional variance of each point is exactly 0. However, the above guarantee requires us to average over these points because our variance prediction on both of these points would be 0. Yet, when we combine these points together, the variance is no longer 0, and it's actually 1/4. And hence, we claim that this is actually not the goal we should aspire to achieve, because not even the true conditional moment functions satisfy this. This effectively stems from the fact that higher moments of a mixture of distributions are not linear in terms of the moments of each underlying distribution. And here's a formula for the moment of a mixture distribution. Note that the final moment here is not linear in terms of the underlying distribution's moments. But if you stare at the formula or at the next equation, the next equation, you will see that moment actually becomes linear in terms of the underlying distribution's moment if they have shared the same exact mean. And this has inspired us to come up with the following definition. Instead of conditioning the points solely on our moment predictions, we also condition the points on the mean predictions as well. So using the same idea of like generalizing the notation, we'll write G mu bar I, mk mu bar mkj to denote all the points in group G whose mean prediction falls in the ith bucket and moment prediction falls in the jth bucket. Then we say the pair of mean and moment predictor together is alpha beta mean conditioned moment multi-calibrated. If the difference in our mean prediction on the set is n most alpha scaled by the measure of the set, and the difference in our moment prediction on the set is n most beta scaled by the measure of the set. And in our paper, we show how to generalize the projected gradient descent approach by Johnson et al. And yeah, although I won't go into the details of the algorithm, at a high level, we're simply alternating the projected gradient descent approach on mean and then the moment prediction. Meaning, at first, we try to make sure there isn't any set of the form G mu bar I bar n k j on which our mean prediction is either overestimating or underestimating by too much. And then we check our moment prediction isn't overestimating or underestimating by too much on the set. The set of the form G mu bar I bar and kj. And you just have to keep repeating this alternating process for some fixed number of rounds before you're guaranteed to have the mean condition moment multi-calibration condition. There's a little bit of complication because the set we're interested in actually depends on the predictor themselves, right? G mu bar I bar m k j depends on mu bar and bar m k. But for the sake of time, I want to talk about how we resolve this complication. But anyway, going back to the doctor and patient story, the patient can now actually interpret this given predictions as valid when average over any of the demographic group that the patient may belong to. So for instance, if the doctor says the ideal stable dosage for a patient is B and the variance is sigma, the patient can say, amongst all people who receive the same predictions as the patient, the ideal dosage for those people was indeed B and the variance was indeed sigma. And also because it's multi-calibrated with respect to some collection of groups, the patient can actually average over any of the demographic group that she belongs to, and the above predictions will still be valid. Finally, I'll quickly talk about how you can form a prediction interval given these multi-calibrated mean and moment predictors. Chebyshev's inequality tells us how we can actually try to bound the tail probability, meaning the probability of how much a point deviates from its mean by its higher moments. And we know that our mean predictors are pretty close to the true mean, and the moment is pretty close to the true moment when averaged over G mu bar I and bar and kj. Therefore, if we had exact multi-calibration, we can guarantee that the probability conditioning on X belonging to set G mu bar I bar and kj, that Y falls outside the given ranges and most delta. Of course, in the case of approximate alpha-beta multi-calibration, we need to widen the prediction by our approximation parameters by a little bit. In fact, if you define delta X like this, you can guarantee that for any set S, as any set G mu bar I bar and kj, where a group actually belongs to one of those collection of groups that we were mean condition moment multi-calibrated to, the probability that the Y falls outside this constructive prediction interval will be at most delta, as long as the measure on the set of points is at least gamma. Finally, going back to the story one more time, the patient will now receive a single prediction interval, and this prediction interval will be a valid marginal prediction interval averaged over any of the groups she belongs to. And hence, unlike before, there's no need to take a union of multiple disjoint intervals. Finally, I just want to note that we have a follow-up work on this idea where we actually try to generalize a lot of the ideas that I've shown you today to an online learning setting, which is different from the setting that we considered because we assume that there is a distribution over the features and the label. And that's it for now, and we hope that this idea of moment multi-calibration can be a useful tool in being able to quantify uncertainty of the model's predictions. Thanks everyone for giving me your attention up until this point, and if you want to see more details, you can find the full paper on arXiv. Thanks.